Okay, so as we start to look at our next module, Module 4 is what we're going to be looking at tonight. Module 4 really boils down to one chapter. It's mostly out of Chapter 3, and there's a couple different specific subjects that we're going to be looking at there. So that's going to be reflected in the practice problems that we end up doing. So as we look here in our learning plan, you're going to notice that we're going to review some sections in in Chapter 13 that we had started looking at in Module 3, but we're going to be going deeper into a couple different things. I also have in here to review the following sections from Chapter 17. Now, Chapter 17, this part was really looking specifically at things like conservation of energy, power, efficiency. That's where we got those equations from. But we are going to be using them here in Chapter 13. So I just have review these things. You don't have to read them. There's no assignments out of Chapter 17, but some of those subjects are going to come up again. The practice problems that we're going to be doing, there's just going to be 3 of them today, and they're going to, mimic 3 different types of problems you're going to be doing for module 4 application problems. So if I go back a level here and we look at those practice problems, they're going to be right here where you would submit oopsie, wrong one. That's module 3. Module 4 practice problems are here. So just the 3, and they're going to be a total of 10 points, just like we normally do. And then application problems, you just have 4 of them, okay? So like I said, each one of the practice problems kind of aligns with what I had picked here. So we'll talk about that as we get into things. So first thing that I want to do is just kind of go over concepts-wise and the sections out of Chapter 13 that we are going to be covering this evening, and then we'll get into the practice problems. So I'm going to use this PowerPoint. Some of these things are going to look a little familiar because, again, we're working from Chapter 13, but we're building on some of these areas and doing some specific problems. So first of all, the approaches. We've been seeing these 2 approaches used most often in the problems that we've been looking at. So looking at Newton's second law, which is the sum of the forces is equal to mass times acceleration. And then we've also been using the work energy theorems as well. Now, and that's with the kinetic energy and work. We're going to be adding in and doing a little bit more in this chapter with the conservation of energy. And we had already kind of dabbled in that, but we'll be adding to that a little bit later. Now, as we look at different elements that we're going to come across in mechanical design, mechanical engineering, a spring is a very popular item that we incorporate into our designs. So this is going to be the section that we look specifically at springs. So first of all, the magnitude of the force exerted on a spring is proportional to its deflection. You probably heard this in physics as Hooke's law, right? Okay. And while we're in what we call the elastic area of our spring, that means that when we apply a load to it and we let go and we take that load off, it's going to bounce back to its original shape. Once we get beyond that, what we call the elastic limit, just like in strength of materials, when you get beyond the elastic limit, all of a sudden you are inducing permanent deformation, and you no longer are going to get the performance out of that material, out of that spring like you did before. Now, I'm just going to kind of relate this. I'm hoping you guys can relate to this, but has anybody ever had a slinky? Remember slinkies? The metal ones were always the best, right? They had plastic ones too, and this could happen to plastic ones. But typically, when I was a kid, and then my kids got them every year in their Easter basket. I don't know why it was an Easter thing, but a slinky was a popular little thing to get at Easter. When we would get them, you play with them, you'd put them down the stairs, right? You would, hold them and go back and forth. But eventually you were like, how far can I pull this apart, right? So you would stand with somebody else and they would hold one end and you would pull it and you would like, oh, okay, we'll put it back together and it's working yet. But you get to that point where you stretch it beyond its elastic limit. And now those little like slinky elements aren't working like they were. You've got like one area that's not laying nice and flat. You can't get it back in the box like it had originally been. That's when, if you would, Hooke's law, when you get beyond that elastic limit and things aren't going to work anymore. So you kind of go beyond the the properties of that material. And what you're doing is you're inducing that permanent deformation by actually pulling it apart enough that the internal molecules or those bonds are actually shifting, and they no longer are going to have the same mechanical properties that they did before. In this case of a slinky, and when there's like thin material, it's easier to do that than when you have thicker material. But as you know, in strength of materials, we're always looking at the internal forces that we have on something and how that is going to perform with the amount of material. It helps us to know how much material by understanding that. So anyway, so spring deflection is proportional to the force that we put on it inside the elastic limit. Beyond that, all bets are off, okay? Now, when we look at work done by a spring, as we know, there is potential energy there, okay? So when we pull on a spring, we have resistance, okay? There's going to be a force that is exerted, and we'll add to our equation sheet. Don't worry about writing these equations down right now, because we'll create it kind of at the end of our concepts here before we start looking at our practice problems to kind of organize these ideas. But when we identify the work that is going to be induced by a spring, we know that the force for work has to be in the same direction as the displacement or the distance for which we are exerting that force over. You're going to notice right here, here is the equation related to springs, where we're going to take 1 minus 1/2 times F1 plus F2. And then we're going to take the distance, or the change in the distance that occurred. Now, F1 and F2 may change depending on where we're at in the spring. So for instance, if we're just starting and pulling it apart, or it's not even being pulled apart, that force is going to be different than when we're actually stretching it further. We can usually feel that difference along the, if you would, the length of, or the deflection of that spring. And then the change in X is basically going to be, well, how far do we actually move that spring with that force? Okay. Notice there's a negative in front of here, and we'll see that and I'll talk about that when we're looking at it in terms of the spring problems that we end up doing for our practice problems, or the one spring problem that we do. So, so we'll kind of save that for that. I'm going to go beyond. Oops, I thought this was going to do that. Well, here's a little question. It says, as the block moves from A0 to A1, or A original to A1. So you're going to notice here on the left-hand side, here's A original, undeformed spring, and then we move it through a distance X1. Is the work positive or negative? Okay, is the work positive or negative? Now, what you want to think about is the direction of the force that is on the body. So you'll notice that the direction of the force is going to the left, right? But the direction of the movement of the spring, the distance through which the work is going to occur, is actually going in the opposite direction. Do you see that? So what do you think the sign of the work is going to be, positive or negative? It's going to be negative. Yeah. So it's going to be negative. Oh, there's a second one here. I gave the answer away. And then as that block moves from A2 to A0, in that case, backwards, what is the work? Is that work positive or negative? So on this side, our force is going in this direction, and it's after we have it completely stretched out. Now we're going to kind of let go a little bit, and that force is going to go to the left. But now you'll notice that our direction of our force is going to go to the left as well. So as we had seen, that's going to be a positive direction of the work. So you have to look at the direction of the force in relationship to the distance for which that force went through. If they are in the same direction, like we saw in the second case, that's positive work. If they are going in opposite directions, then it would be negative work. Okay. Work of a force. So does a normal force do work on a block that slides from A to B? So if we're on a surface here, so here's A, we're going up the incline. Does the normal force do work? The normal force is the one that supports it on that surface. I'm seeing a lot of heads going, no. Christian. Exactly. The distance doesn't change. So the normal force, the one that's perpendicular to the surface it's riding on, not doing work, right? Not doing work. But does the force, or I'm sorry, does the weight do work on the block as it slides from B to A? I see yeses in the room. Let me see the chat. I've got a couple chat. Yes, yes, yes. It does. It absolutely does. Now, we might say, well, the weight itself is going down and this is at an incline, but we would have a component that would go along that direction. Now, the question is it in a positive or a negative direction as we go from A up to B? Is that work positive or negative? Lex says negative. Anybody have a virtual? Anybody positive or negative on the work? We'll see in a little bit. Okay. Nobody wants to chime in. It was positive, but let's look first. So does the normal force do work? No. Does the weight of the block do work on going from B to A, or going from, oh, you know what? From B to A, it would be yes. Lex, you were correct. I was saying A to B, right? I was going up the incline. That would be negative work, but I didn't read that close enough. I'm so sorry. From B to A going down is positive work because they're going in the same direction. If we're going up the incline, that would be negative work because the direction of the component of the force of weight is going to be going in the opposite direction of the actual movement itself. So you answered it correctly. Aaliyah, you answered it correctly too, the way that I said it. Then as we look here, the principle of work and energy. So as we know, the work energy theorem says that if we take our kinetic energy before and after, that is going to be equal to the amount of work that we do. So we have been, seeing this concept play out in a number of different scenarios, and we're going to see it here again in chapter 13, the work that we do here. Now, we did introduce this in chapter 17, but power and efficiency, but we didn't really do I don't think we did any problems with it, actually. We are going to be using it here in chapter 13. So power is going to be equal to, and there's two things that we can do. And again, we'll write these down more organized on our equation sheet. But the most popular one is going to be force times velocity. So if I know the force that something is, I can multiply it by its velocity, and that's going to give me the power. Now, power is also defined as the amount of time it takes to do work. So if we know how much work a certain force did, and we divide it by the amount of time that it took to do that, that's also another way to get at power as well. So we'll have two equations related to power. Now, as we look at the dimensions or the units for power, very popular is the watt or the kilowatt. Those are going to be the units in the metric system, and that's going to be a Newton meter per second. Okay, so that's going to be a joule per second, Newton meter per second, and then a kilowatt is going to be 1,000 watts. Now, in the English system, we can't make this easy because see all the ones here. 1 horsepower, we are in horsepower, we say that's 550 pound-feet per second, okay? Which is also equal to 746 watts if we wanted to convert back to the metric system. But we always report in horsepower, and the units that we get from the problem are going to be in foot-pounds per second. So there's 550 foot-pounds per second in 1 horsepower. And then efficiency is going to come up in our problems, our practice problems today, and then also our application problems, where we look at efficiency is going to be the total output work or power divided by the input work or power that we put into the system. So, so that's kind of the nutshell of the equations that we're going to be looking at. Before we start getting into our sample problems, which is our next slide here, what I would like to do is let's go ahead and generate our equation sheet and organize the things that are going to come in handy. I'm not going to say it's going to be a completely exhaustive list, but I tried to kind of gather the items that that are going to come in most handy for Module 4. So I'm just going to call this Module 4 equations. And again, some of these, as we saw, are going to be repeats, but some of them are going to be a little bit newer to us. So the first section that I kind of put this into is I wanted a section on my equation sheet related to springs, okay? Now, first of all, a spring is going to be identified with what we call a spring constant. So knowing that you all have had physics before, I'm certain you've done labs and looked at springs, you know, in at least a couple places. So we can say that the force that we put on a spring is going to be equal to the spring constant K times the distance for which it's stretched, okay? So over here, I can say that F is equal to force to compress or stretch, okay, on the spring, depending on the type of spring that we have. I'll go. No. No. And then K is going to be your spring constant. It would be positive or negative depending if it's a compression or an extension spring in relationship to the movement that's created. It can be, yes, it would be based on the problem. So K is our spring constant. Somebody in the room asked, shouldn't it be negative? And I'm like, nope, nope. X is going to be our distance or deformation, sometimes referred to as, okay? Now, as far as units, okay, the units for force, what are we expecting for units for force? Newtons, if we're in the metric system, right? Okay, what else? Pounds would be the units in the English system, okay? So if you are given in kilonewtons, you want to put it into newtons for all of our problems. So you're going to have to maybe do a little converting. If you're given, we're not in any of our problems, a kip. Remember, a kip is 1,000 pounds. That was from statics and strength of materials. Remember that? Yeah. No. K is going to be our spring constant. K is going to have units of force over time or over distance. So for instance, in the metric system, it's going to be newtons per meter. Okay. In the English system, it's going to be pounds per foot. Okay. And again, it's important to know the units because I'm not having you put them throughout the problem. I might rethink that for next year. I hate it because I put them in all the time when I work it just to be sure everything is coming out and that the numbers are right. And if I do forget something or if something doesn't come out, it's usually in the units. It's usually in there. So so you guys might have dodged a bullet. But I also realize, especially some of these equations are quite lengthy. To get all the units in there too is going to be a little bit challenging. I enjoy them too, Aaliyah. I get it. I'm there with you. X, this is going to be simply a distance. So it's going to be meters or feet. Okay. So that's our spring constant. When you're given a spring constant, it's going to be in, 20 newtons per meter. And all that really means for that spring is that that's how much it's going to move, per unit of force. Okay. Now, as we look at springs, we have two equations for work, as we kind of alluded to. So the first one, we're going to call it U1 to 2, and we're going to, in parentheses, and then in back of it, we're going to put a lowercase e. This is for elastic work done by a spring, okay? And this is going to be equal to 1/2 K, which is the spring constant, times x1 squared, okay, minus 1/2 K, same spring, x2 squared. So initial and final positions. Okay. You can condense that and say 1/2 K times change in x squared. This one here, it's a lowercase e for elastic work. So it's work due to a spring. Okay. Now the other equation that we can use, 1 to 2. So this would be an or, okay? Or if we expand that out, we can say 1/2 times F1 plus F2. Those would be the forces times the change in X. Okay. So X1 would equal initial position. X2 is going to be final position. So that's kind of the spring stuff, okay? And I'll put work here. All right. Then another type of a problem that we're going to be looking at is roller coasters. I think it's important, right? In physics, you always do roller coaster problems, right? We can relate to them, go on the rides, go to Great America. You can think about the math involved. And so we have a couple of roller coaster problems we're going to be doing. And I'm going to ask you, if you remember doing roller coaster problems, what type of approach did you take to roller coaster problems? Yeah, approach. Right. Yeah, we'll be doing that. Yep, kind of a start and a finish. Yep, go ahead.
The initial energy and final energy.
Yeah, so conservation of energy, right? Conservation of energy. So we're going to be using the conservation of energy. Okay, and you're right. We're looking at the before and the after. Okay, so this is going to be classic roller coasters. Which are fun. Okay. So T1 plus capital V1 is going to be equal to, so this is our, one side of our energy, and T2 plus V2. Remembering that T is equal to, and I'm going to put KE for kinetic energy, whether it's initial, which are the ones, and finals, which are the twos. Capital V is going to be our potential energy. Okay. Again, initial and final. Now, we can break our potential energy into two things. So I'm going to kind of put the T1 out here, plus we can have gravitational potential energy, and we can also have elastic potential energy, okay? And then equal to T2 plus, and then we would have VG2 plus VG1. So again, I'm sorry, VE1, VE2, VE2. These are twos on the right-hand side. So gravitational, elastic, gravitational, elastic. So before and after, or initial and final. Yeah, so gravitational and elastic. Now, as we look at calculating gravitational, we are going to find that gravitational is equal to mgh, which should sound familiar. And when we look at potential energy, this is going to be the force, if you would, and then times h, which is the distance, okay? When we look at work gravitational, let's see, U1 to 2, okay? Gravitational, that's going to be equal to the potential energy gravity 1 minus potential energy gravity 2. So just the difference between the gravitational potential energies will get us the work done on that. Right. So that's the conservation of energy, kind of roller coastery types of things. Okay. And then the next section that I have here is power and efficiency. Okay, power and efficiency. So first of all, as we said, power is going to be equal to force times velocity. Okay. It's also going to be equal to the work done divided by the amount of time. And we can also say that this is mgh when it's due to potential energy divided by time as well. Okay. So kind of three options. Now, efficiency, that's this like cursive N, if you would. That's what we see a lot for efficiency, is going to be the work out divided by the work in. And then we can also do power out divided by power in. Now, this number is always going to be less than 1 because it's very seldom that we have 100% efficiency because there's always losses in a system from before to after or in to out. And if it is greater than 100, then we're breaking the conservation of energy law, right? And that's hasn't been found to be possible at this time. Now, additionally, there's going to be a problem where you need to determine the percent change. Okay, so percent change, let's see, there's an N in there. It's going to be equal to, I'm going to do it like this, %1 plus %2 divided by %1. Okay. We'll be using that in one of our problems. And then just a reminder that the units are watts. Okay. 1 watt is equal to a joule per second is equal to a Newton meter per second. Okay. And 1 horsepower is equal to 550 foot-pounds per second. Okay. Now, those are, if you would, kind of the basics of the concepts that we have in Chapter 13 that we'll be using for practice problems and the application problems, okay? See some people writing yet, so I want to make sure that because I'm gonna be turning my paper over. We've got a couple more things to add here that are gonna come in handy, okay? All right, so as I turn over, got a couple other ones that I want to add here. Actually, one more equation, but then a couple other concepts. So the next one is going to be normal acceleration. Now, the reason I'm putting this one here is just because it comes up when we do our roller coaster problems. The normal acceleration is going to be equal to velocity squared divided by the radius to the curvature, okay? And is that rho? Is that what you said, James? Rho, that's rho. I always think it's phi, but rho is going to be that radius of curvature, okay, of the curve. No, I think I know you're right. Yeah. And then V is our velocity. Now, this is going to come in when we go around curves. So for instance, on those roller coaster problems, when we're going, around a loop to loop, or we're going over a hill, there's going to be a curve involved in that. And that normal acceleration is the acceleration that we're going to be using for those items. Okay. And I mean, that was kind of, if I remember correctly, that was like one of the equations that we had to kind of think back to, previous. Probably the other one that I didn't add here, and I probably should put it over here in conservation of energy. This is one I think that we've got down, but we know that T is equal to 1/2 mv squared. I mean, that's still valid here, and that's going to continue to come up, but I think that one might be like in our brain permanently now because we've been using that a lot. So that is another one that'll come in handy. Now, additionally, what I have written down here, couple things. Weight, okay? Okay. Weight in the metric system. I always like to do WT for weight. They'll do W, capital W a lot in our textbook. I like to, and again, I know they're not using capital W for work in this book, but to me that's work. Okay. So I usually do WT for weight. In the metric system and in the English, it's always mass times gravity. Okay. Now, metric units. Okay. That means that we're going to have kilograms for the mass, and we're going to multiply it by meters per second squared. Okay. That is equal to a Newton. All right. That's equal to a Newton. So when we take mass times gravity, yes, we have kilograms times meters per second squared, but that combined, kilogram meter per second squared is a Newton. All right. So if you see a Newton, and probably I'm sure in physics, you got the opportunity to expand that out when you needed to get the cancellation of the units and such. Yes. I'm going to get there. You are like on it. So English, let's do weight for English. Okay. So WT here, still going to be mass times gravity. Okay. Now, mass in the English system is called a slug. All right. But we never hear it. And we actually really never deal with mass except when we have to kind of manipulate it here. The units for mass are the pound second squared per foot. So you never heard of it, right? We don't use it. Pound second squared. I'll zoom in here. Pound second squared per foot. That's the units for mass. That's a slug. Okay, and that's a slug. And then we multiply that by gravity, which is feet per second squared. And when we multiply those two together, you're going to notice, what do we have? Cancellation of units here. And what do we end up with? A pound is going to be the units for weight. Okay. So if you see something called out as a pound, because in a problem, it's not going to say the weight of the block is, it usually says 25-pound block. Or in the metric system, it'll say a 50-kilogram block. And that's where I think it can be confusing, because when we see kilograms, that's mass. So then if we need the force due to the weight, then we have to multiply by gravity to get the weight. But in the English system, we're going to be given pounds. We're going to be given weight. And then if we need mass, we've always got to divide by gravity by the 32.2. So we want to also say gravity here in the metric system line is 9.81 meters per second squared. And gravity here in the English line is 32.2. Now, I used to teach physics, as you know, at the other college that I was at. So I always kind of knew, where we were at. So I assume that that's there. And I'm sure that you've covered it, but I did see a little bit, and more than a couple times where like this was mixed up sometimes, like putting pounds, like the weight where there was mass, or using the kilograms where it would have been, a force should have been used. So not a huge deal. Oh, feet. Thank you. Thank you, William. Yep. Here we go. In the English units, feet per second squared. I appreciate that. Thank you. Sorry. All right. And then it's also important, like I said to you, I might go back on this. We might put units back in, but as we're going through, and there's a couple places in the problems that we have for this particular module, we've got to make sure that our units are what they're supposed to be. So for instance, if I'm dealing with, and I'm just going to do some kind of a units roundup here. So acceleration, A. Okay, units for acceleration are going to be meters per second squared in the metric system and feet per second squared in the English system. Okay, those are going to be the units that we're going to use for. So if you're given acceleration in some other form, millimeters per second squared, you got to make sure it's in meters per second squared. For velocity, that's going to be meters per second for the English system. Or I'm sorry, for the metric, and it's going to be feet per second for the English. So if you get it in inches per second, or if you get it in kilometers per hour, you've got to change it, okay? So that it fits in with what we're using. Work, okay? Units of work are going to be the Newton meter which is also equal to a joule in the metric system. In the English system, it's simply going to be pound, feet, or foot pounds, whichever way you prefer to say it. Kinetic energy, same thing. Newton meters, which are equal to a joule, and pound, feet, or foot pounds in the English. Potential energy, I'm just going to use my little quotes here because that is the same as it is for potential or for kinetic energy. And then power is going to be the watt. I always write out watts. You're not going to see it done that way in our textbook. They usually, like for a kilowatt, for instance, they're going to do KW, capital W. But again, be careful with that capital W because it's used in other places as other variables. And sometimes it gets, I don't know, I think it can be forgotten that those are units. So I usually write out watts, which is equal to a Newton meter per second. Okay, or you could have a kilowatt with a K in front. And then for our English system, it's going to be pound feet per second. Okay. So if time is given in a minute, you got to get it to seconds. If distance is given in millimeters, you got to get it to meters, okay, when you use it in the problem so that you end up with the right units available at the end. So any questions on that? That should be review. Okay. All right. So with that, if we've got our equation sheet kind of all set, I think we are ready to look at our first application problem. Okay. So I'm going to pull this away. I'm going to go back underneath to our PowerPoint. And we are now ready for sample problem 13.3. If you're in the textbook, this is on page 811. Okay. So what we have here is we have a spring. It's used to stop a 60 kilogram package, which is sliding on a horizontal surface towards it. The spring has a spring constant K of 20 kilonewtons per meter. Okay. Kilonewtons per meter. So if you recall from our equation sheet, this needs to be in newtons per meter. So we're gonna have to do a little bit of converting when we deal with that. And it is held by cables so that its initial compressed distance is 120 millimeters. The package has a velocity of 2.5 meters per second in the position shown. Determine the coefficient of friction, kinetic friction between the package and the surface, and the velocity of the package as it passes again through the position shown. So we're actually going to be showing this or looking at this in 3 positions. Position 1 is as the package is going to be moving to the right. Position 2 is going to be at the maximum deflection of the spring where it actually stops, if you would, before it starts going back in the opposite direction. And then position 3 is going to be moving in the opposite direction back in the same place that position 1 was. Does that make sense? So we're going in, compressing, and coming back out. Okay. So let's take a look at how we are going to approach this. We'll kind of write down our knowns and what we're going to find. Like we normally do. So this is sample problem 3.3. Okay. And what we know that the K of this spring, it's set in the problem 20 kilonewtons per meter. Okay. So 20 kilonewtons per meter. I'm going to say equal to, and the number we're going to use in our problem is going to be the newtons per meter. So we have to multiply that by 1,000. So that's going to be 20,000 newtons per meter, because those are the units that we need to use for K in the problem itself. We know that the mass of that block is 60 kilograms. Okay. We know that the distance that we're going to be covering, okay, is going to be 600 millimeters, but distances need to be in meters. So that's going to be 0.6 meters. Okay. I like to kind of get these things out there right away. That way I don't have to try to remember it later on. I also know that the original compressed length of that spring was 120 millimeters. That's going to be 0.12 meters. I also know that my velocity original or one, I'm going to say velocity one because we're calling that position one. I know that's 2.5 meters per second, which are the appropriate units. Now, I'm going to have to find, as it says in the problem, I'm going to have to find part A. I want to know what the coefficient of kinetic friction is at the place when we have an additional deformation of 40 millimeters. Okay, and what that means is, we go back to the problem. Right now, this is held in compression so that this right here is 120 millimeters deep. Okay, from the wall to where the spring is held. We want to go another 40 millimeters to the right. That's what it's telling us. Okay. And we can say that's equal to 0.04 meters if you want to convert that right away. And then part B says, what is our velocity at position 3? So it's coming back in the opposite direction at that same placement that 1 was, but going opposite as it comes off of that spring. Okay. So the approach we're going to take is going to be equal to work energy theorem. Okay. We want to find a velocity, got some distances, so it makes sense. So we know that work energy theorem is going to be T1 plus the work done between 1 and 2, positions 1 and 2 is equal to T2. Okay. Now this is for part A because we're only looking at part A, and I'll put that right here, part A, where we're looking from position 1 to position 2, because that's where we're going to determine the coefficient of friction. Part B is going to be looking from 2 to 3. Okay, so we will be looking at that at that second section a little bit differently. Now, because of what's at play here, okay, we have a couple things that we need to do here. I'm going to expand out my work energy theorem. I'm going to say T1, which is our kinetic energy 1, plus. Now I'm going to take that work and I'm going to break it into the work from the friction force, because the friction force is, if you would, causing negative work. It's taking away from, moving in that direction. So this is going to be the work due to, and I'm going to put FF friction force. And then we're also going to have work due to the elasticity of the spring. And then equal to T2. Okay. Now, as we look at from position 1 to position 2, so again, if we look back at our illustration, position 1 is on the left-hand side where the package is in the position we see here. Position 2 is going to be when it stops and is done compressing 40 millimeters in from where it's at on that spring. That's position 2. At that point, at position 2, the kinetic energy is going to be 0. Okay, because it's stopping, right? It's compressing to the 40 millimeters, and then it's going to be stopping because then it's going to be going back to changing its direction. Okay, so we can say that, we go back underneath here, T2 is equal to 0 because V2 would be 0. Everybody follow that at that position? Okay. All right. So now our responsibility is to kind of get all of the other elements so that we can plug this in. Okay. So the first thing I'm going to look at is going to be my T1. Okay. T1. T1 is the kinetic energy of the package right now in position 1. We know that it's moving at 2.5 meters per second to the right. We are going to, for the problem, for the entire problem, and I guess I'm going to put this up here. I haven't been super diligent on this, but I always like to keep our standard convention of positive up and to the right, unless otherwise necessary. In some cases, you might want to change it, but for the most part, we stick with that. So we're going to the right here. So that means that our kinetic energy is going to be a positive 1/2 mv squared. Okay. So we would just simply put our values in here, 1/2 times the package is 60 kilograms. And then the velocity that that package is going at is 2.5 meters per second. Well, you don't have to put the meters per second in, sorry. Such a bad habit that I have. We're going to square that. Okay. So that means our T1 is going to be equal to, you should get 187.5, and the units here would be meters per second. I'm going to put my little cloud around that because it's something I'm going to go back to, but it's not a final answer. Okay. No, Newton meters. I'm already thinking ahead to my velocity later on. Okay, sorry, thank you. Newton meters. Okay. Or joules, you're correct. The next part that I have here is going to be the work done by the friction force, okay? So I am going to draw my block, okay? And I know that on my block, I have the weight of my block, WT, going down, and I have a normal force going up, right? Now, this is going to be moving to the right, okay? So I know that I don't have a place to put it. My velocity 1 is moving to the right. So that means that in this case, going from position 1 to position 2, my friction force is going to impede motion. So my friction force is going to go to the left, okay? I know my friction force is going to be equal to the kinetic energy or the kinetic coefficient times the normal force, all right? So that means 2 sum my forces in the y equals 0 because it's not moving or there's no acceleration vertically, okay, the way that the motion is. So I'm going to say sum of my forces in the y equals 0. So in this case, I have negative WT plus N is equal to 0. Solving for N is going to be equal to, I'm going to put my weight on the other side, right? And my weight is equal to 60 kilograms times 9.81 meters per second squared. I'm putting that in there so you can see that that is the mass times gravity. That's what the 60 times 9.81 is. So my normal force is going to be 588.6 newtons. Okay. Now, that's not what I'm looking for here. I want my friction force. Okay. And I want my friction force because I'm going to be able to use that for the work done by that friction force, or the negative work done. So friction force here then, it's going to be kinetic coefficient times, parentheses here, 588.6 newtons, okay? Or you don't need the newtons. So I can say that my friction force is equal to the coefficient of friction times 588.6, okay? And that's going to be, and I'll put newtons in back there. And that's going to be then the value that I plug in when I need that friction force, which I'm going to need shortly. Now, if I look at the work that's done, I know that work is always going to be force times the distance for which that force moves through, okay? So as I look here at my friction force, the work that's going to be done, or the friction force is going to impede, I'm going to look back at my original illustration. It's going to work over a distance of 600 millimeters plus, remember, there's another 40 millimeters that we're going to compress this in, and that package is in contact with that surface during that entire time. So, oopsie. So that means that our work 1 to 2 due to the friction force, okay, is going to be equal to negative, because again, my work is being done, my distance is going to the right, but this force is acting to the left. So it's a negative. It's going to be friction force times the distance x, or the total distance x. And I'm going to say total. okay? So this is going to be a negative coefficient of static friction times 588.6, okay? Times the total distance of 0.6 meters plus 0.04 meters, okay? It is the distance between to the spring and then the compression of the spring for 40 millimeters in, or 0.04 meters, okay? So a total distance of 0.64 meters, all right? And again, the negative on the work, because it's the force is pointing in the opposite direction. So that means that our work 1 to 2 due to the friction force is going to be a negative, okay, 376.7, and then multiply by the coefficient of friction. I'm sorry, yeah, the coefficient of kinetic friction. Okay. Questions so far? We're following? All right, so what we've done so far is, if we go back up here, we did my T1, and we just got done with the work due to the friction force. Now we've got to do the work due to the spring, the elastic work. Okay, that's done. So now what we're going to do is we are going to take U1 to 2, and this is going to be E for the elastic work. And this is going to be equal to a negative 1/2 times, in our equation, where was it? It was up here. This was F1 plus F2, okay? F1 plus F2. We are going to call this P min and P max, okay? P min plus P max, okay? And all that is it's, instead of using F, because they used F as a friction force, they're now using P as the spring force that's going to actually push the package to the left, okay? So when it hits the spring, okay, so here's the spring right here, that is going to be the force that actually is going to be pushing it in the opposite direction. Now it's negative because of the direction of the P, as we see here, okay? And someone asked earlier about negative with springs. It just depends if it's a compression spring or if it's an elastic, and we have to compare the direction of the force to the direction of the motion that we go through. Okay. Now, P min and P max, okay? These are forces. So it's basically, instead of using F, we're going to use P. It's going to be equal to K, the spring constant, times the distance, okay? So P min, let's look at that one first. P min is going to be equal to K times the original compressed length, okay? So our K, we know from up here, we're going to use the 20,000 newtons per meter, and the original compressed length was 0.12 meters, okay? So this is going to be equal to 20,000 times 0.12. So our P min is going to be 2,400 newtons, okay? P max, okay? P max is going to be, when we compress it, another 40 millimeters, but this is what we would call a preload, okay? So remember from the beginning, what they've done on this spring is they've actually compressed it an amount, okay? And that's what you see here with a cable, a certain distance. This distance right here is 120. So it's already preloaded, and that's what we just calculated with that minimum force on that spring, okay? Yes.
Sorry, the work done on the spring is negative because it's going in the opposite direction of the box pushing it.
So the question in class is the negative on the work here. So as you look here, you're going to notice that this is going to continue to move to the right, okay? as it hits that spring. The spring is going to be pushing back with a P. So that means that it's giving us negative work because the motion is going opposite the direction of the force. Yeah. Good question. So now P max is going to take that preload, the P min, and now it's going to add to it how much force it's going to see based on compressing it an additional 40 millimeters. So P max is going to be equal to P min plus K, and we're going to call that, what did I call it? Delta X, sorry. No. What did I do with, I don't think I identified. What do we want to call that? X1. Yeah, okay. XO and X1. Sure. Yeah, we'll do that. XO and X1. And that's going to be our 40 millimeters. So we're going to take our 2,400 newtons. Let's put this up a little closer. That's going to be our P min plus 20,000 times 0.04 meters for the additional 40 millimeter compression. So our P max should come out to be 3,200 newtons. Okay, I'm gonna hope I can get this in here rather than turning the page here. So now I want to do my work 1 to 2 elastic is going to be equal to -1/2 times P min, which is the 2,400 newtons plus 3,200 newtons times. Now, what's going to happen here is we're gonna compress it. It's the change in X that we have here. Change in X at the end of that equation. I forgot to add that. And that's going to be 0.04 meters. Because that's when it hits and it's going to go that additional amount. So our work done by our spring to 2E is going to be equal to, should come out to be a -112 Newton meters. And I'll put my little cloud around there. And that's going to be then the work done elastic. Okay, so I want to be sure you guys saw that there. So I kind of did my P-mins over here, and then I used them in this equation. And I have a -112 Newton meters as my elastic work done by the spring as it compresses into that additional 40. Okay.
You don't count the preload for this one.
No, because it's already there. So for this one, when we do the work, so when it hits, it's already preloaded, right? So we're looking at the distance that when it hits the spring right here, all it's doing is it's moving another 40 to compress it an additional. So we don't add the 120 in there. It's just 40 as it moves. Okay. So now I'm going to have to turn over here, and we are going to now use these values in this equation up here, because we have them all calculated, and our only unknown should be that coefficient of kinetic friction. So I'm just going to do T1 plus U1 to 2 based on the friction force plus the work elastic due to that spring plus T2, which we know is 0. Okay. I'm just rewriting that equation. So T1, if I go back on the other side, T1 was 187.5 Newton meters. So this is going to be 187.5. And that's Newton meters, but I'm not going to put the units in. My friction force, okay, it says plus the friction force, but my friction force, the work done by my friction force was a -376.7. So, and then it's multiplied by the kinetic friction coefficient. So we're going to do a minus, okay, 376.7. And that is going to have the coefficient of friction kinetic variable attached to it. And then we're going to do the elastic work. We found that to be at the very bottom down here, a negative 112. Okay. Equal to 0. Okay. So now it looks like we can combine the 187.5 and the 112 and solve for our coefficient of kinetic friction. So we're going to end up with a 376.7 times the coefficient is going to be equal to, moving that to the other side, a negative 75.5. Both sides become positive, and then we can divide both sides by the 376.7, and our coefficient of kinetic friction is going to be 0.2. Part A. Any questions on that one? Okay. Part B. Okay. Part B. Now we're going to be dealing with position 3. Okay. So this is going to be position 3. Okay. And what I'm going to do is I'm going to draw kind of a sketch of what we have. So this is position 2. So we're going to call this V2 is equal to 0. So this is position 2. As it hits the spring, compresses it the 40 millimeters, and now it's at that position right there that it's just ready to change direction. Okay, so it's a velocity of 0 at that point. Okay, that's position 2. Now it's going to start going back in the opposite direction. So on our package, we're going to have that P force, that spring force that is pushing it to go to the left. It's also moving to the left. So it is going to have a velocity 3 going to the left. And that's what we need to find, right? And we want to find it at the same position as position 1. So if we look to position 1, we know that that was 600 millimeters between, but then plus 40 millimeters to the maximum deflection of that spring. So our total distance coming back is going to be the 640 because it's compressed at 40 into the spring and it's coming back the full 600. Does that make sense to everybody? Okay. Now, as it's moving backwards, there's a friction force there, but since it's moving to the right, the friction force direction changes. So the FF is going to be going to the right. So it's moving to the left. Friction force then is going to impede on motion. So it's going to be now going in the opposite direction. Now, same surface, same package. So we'll be able to calculate the friction, the actual magnitude of the friction force this time because we know what the coefficient of kinetic friction is, right? Okay. So as we look, we're going to use again the work energy theorem here. Okay. So we know that T1 plus our work. Now this actually, I'm going to change my variables. I'm so sorry. T2 plus the work from 2 to 3, okay, is going to be equal to T3, right? Now, we know that T2 starts right here. The velocity 2 was 0, right? Because that's where we're changing our position. So T2, our kinetic energy at position 2 is going to go to 0, right? We also know that based on when it went from 1 to 2, that there was friction force work and there was also elastic work. Those are present again. So we are going to expand this then, okay, where, give me a little bit more room. This is going to be U 2 to 3, and this is going to be the friction force plus U 2 to 3 for the elastic spring force is going to be equal to T3. So these are the three parts that then we have to now calculate for finding the velocity 3. Okay. Now, we can make some assumptions here based on the work that we just did from part 1 to 2, or position 1 to 2. I'm going to put my convention back in place here, where to the right and up is going to be positive. I can say that the work from 1 to 2 due to the friction force is going to be the same magnitude as work 2 to 3 friction force, okay? So that's going to be equal to, and we'll give the sign a little bit later, that's going to be equal to 376.7 times the coefficient of kinetic friction, okay? We know that to be 376.7 times 0.2. So that means that our U 2 to 3 friction force, oh shoots, wait. I didn't do that right. Oh no, that's correct. I'm sorry. I'm sorry. So that means multiplying those together, U 2 to 3 friction force work is going to be 75.5 Newton meters. Okay. Now, you're going to notice that the direction of that force, friction force, is going to the right. So we're going to use that same convention that we normally do, going to the right. Now we're going to find the work done by that elastic force. And we can say that the work done by the elastic force from position 1 to 2 is going to be the same magnitude as 2 to 3. Okay. And we know that to be 112 Newton meters. Okay. And that was from bottom down here. Okay. Now we're going to use that equation there. So we can say U 2 to 3 friction force plus our work 2 to 3 elastic is equal to T2. Okay. And now we know this value to be 75.5 Newton meters for our friction force. And because this is going in the opposite direction to the left, our convention says to the right is positive. So this is going to be a minus 112 Newton meters. It's going to be equal to our kinetic energy is going to be 1/2 times the mass. The mass of that package is 60 kilograms. And then we're going to multiply it by velocity 3 squared. So our only unknown here is going to be the velocity at position 3. Okay. So if we solve here, we're going to end up with 36.5 divided by 30. It's going to be equal to our V3 squared. So taking the square root of that, our V3 is going to be equal to a negative 1.103 meters per second. So this is going to be negative under the radical, but if you take a square root of a negative, you're going to get an error. So you have to make the velocity negative. And it makes sense because according to our convention, going to the right is positive. That negative just means that it's going to the left. Okay. And that is the velocity that it would come back at in position number 3. So if we go here in position 3, this is going back to the left, and that's where it would be at that point. Okay, any questions on our first problem? Kind of two distinct problems in this one. So I am gonna stop the oh, Lex,
We use a lot of like letters.
I know.
If we make it consistent, like I said, spring forest using P, can we just use like F, well, like subscript F?
Oh, yeah. So I just stuck with what they used in the example. So the question that Lex has was, instead of using P for the spring force, could you use, let's say, F sub X? Because
Yes.
friction force is F sub F, right? Could we use F sub S for the spring force? Absolutely. Yeah. Other questions? They randomly pick variables, I noticed, but yeah, that's okay. We'll adapt. We can do it. All right. If there's no other questions, then I'm going to stop this recording.